Last time we discussed the thermodynamics relationship, which is an equation relating the change in density to the change in temperature and pressure. And today we'll be discussing the thermodynamics equation, which is an equation that's commonly used in numerical models for predicting temperature. So if you want to see an example of this, you can go to windy.com and you can see, the wind speed. You can also see the temperature predicted for the next 1 to 2 weeks at 3-hour intervals. You can see for the entire globe what the temperature is, and that temperature that you'll see there is what is calculated commonly by this equation. And so there's two main variables we need to know. One is energy E and heat Q, which are both have the same units. And the first law of thermodynamics then tells us that the change in energy plus P change in specific volume is equal to the change in heat. And we can then use, from the last video we discussed the chain rule. We have that d ln alpha is equal to 1 over alpha d alpha, or d alpha is equal to alpha d ln alpha. So we use that to convert this term into this term, which will later prove to simplify our equation in a really nice way. And so next we remember that we have this equation for d ln alpha from previously, which we can plug into this equation, and then that will return us this, which is d energy plus P alpha isobaric expansion term dt plus P alpha isothermal expansion term dP is equal to dQ. And now you can see why we did this simplification here is because we can now get these terms here, which we will use later. Now we can come up with a term called, which I call constant volume specific heat, thus the V here, which is a term that we have calculated in laboratory through experiments over many generations of researchers. And so it's useful because we can get rid of the E and replace it with a constant times the change in temperature, which is a variable that we can actually calculate. Satellites can calculate temperature recently, so that it's more useful to use that. So we can define our CV as dQd temperature holding specific volume constant, and if you were to do that in this equation holding this term constant, we could then get that it's not only equal to dQ dt, it's also equal to dE dt. And doing that, we can now multiply T on both sides, and we'll get that dE is equal to CV dt, and we can plug that in here. Next, we can take out, we can take terms that have dt, and we can distribute them into this term, take the dt out, and then we have this term here, dP equals dQ. And now we can, for our next step, we can also create a term that I call constant pressure specific heat, and that term, using the equation above, we can take dt on both sides. So we have dt here and dt. And so you'll find that this term goes away because P and T are not dependent on each other. They're separate in a way, and this will become 0. And dt dt is 1, dt dt again is 1. And so we're left with Cp is equal to Cv plus P alpha times the isobaric expansion term. And this term we know from previous video that it's equal to 1 over temperature, and we know that from the equation of state, which says P is equal to rho r dt, or if we divide rho on both sides, we have P alpha is equal to RdT. We can sub that in here, and then now dividing the temperature out, we will get that Cp is equal to Cv plus Rd, which is a very useful equation that can be later used in thermodynamics. Now, returning back to our equation here, we notice that this term, as we just found, was equal to Rd. So we have Cv plus Rd, so we can replace this entire term here with Cp. So we're basically removing this complicated term with a term that we have calculated more in lab experiments, that is holding pressure constant, the change in heat over unit temperature. So now we're left with Cp dt plus P times the isothermal expansion term times dP is equal to dQ. And now using from equation of state, we have that this term is equal to -1 over P. So crossing P out and turning this into a negative sign, we will be left with Cp dt minus alpha dP is equal to dQ, where again Cp is the specific heat holding a pressure constant, and specific heat is basically the heat needed to heat something up to a certain amount. And we can then divide that by T to get a temperature tendency equation, which is Cp dt d time minus alpha dP dt equals dQ dt. And we can compare that to the equation from before, which is, let me just go back, which is this equation here. We could, we rearranged this equation. Another episode is d ln T is equal to dt is equal to d ln P dt minus, sorry, hold on, that's a plus, yeah, it'll be minus d ln rho dt. And so, and I apologize, this is time here. We can see that comparing these two equations, we have actually removed, we have density, which is because alpha is equal to 1 over density, but we do not have the change in density to worry about in this equation. But it also gives us this heat tendency term, where tendency just means taking the derivative over time. This heat derivative, which will allow us to look into some more complicated things that occur in nature that can change the heat term in this equation. Some you can have the change in heat as 0, but we have other situations such as solar radiation is a big one that will change the heat, and also there's some microphysics processes such as condensation, precipitation, evaporation that can also affect the heating term. But that's that for now, and in the future we'll be talking about thermodynamics for moist air, or moist thermodynamics.